Okay. All right. So uh, in this video, I'm going to work on some exponential logarithmic problems. Okay. So here's where I noticed a lot of work on the test itself that looked like you really just jumped from beginning to end, or you didn't really have a good understanding of it and you're trying to follow, some unauthorized resource. So please use my examples and try to make sense of it. Okay, on 42, what I notice is that 16 and 256, I think those could both be made to be 2 to some power. So I check on that and I find out 16 is 2 to the 4th. 256, if I divide, 256 by 2, I get to 128. I can keep going a whole bunch. Now I'm down to some I already know. I already know this one is 5 2s. So I have 1, 2, 3, 4, 5, 6, 7, 8. So 256 is 2 to the 8th. So I get suspicious on ones like that maybe I can get the base to be the same. Okay, but you got to be careful. This is the step people are leaving out. And if you do, I'm not giving you full credit. Okay. You got to show me what these exponents become so I can really kind of see what you're thinking. So this is a power raised to a power. So this is going to become 2 to the 4x plus 12. And then over here, it's going to be 2 to the 8x minus 16. Okay? All right, now, if the bases are the same, then you know these exponents have to be the same. There's no other choice. You also could think about it by thinking about doing log base 2 on each side. And that's another way to think about what has happened to the 2. I didn't divide it. Okay. I undid it. I did the inverse of it. So these undo each other. And these undo each other. And so we get to the point where the exponents are equal. So the explanation typically just leaves that step out. If these two bases are the same, then you know those and you got an equal sign between them. You know that the exponents have to be equal, right? And then that I think you can finish up. I'll finish it. You're going to subtract 8x, get a negative 4x plus 12 equals negative 16. It's just a linear equation. So I'll subtract 12, divide by negative 4, and then I do need to think on this whole unit. Sometimes you got to check these. This one you could check to see if you're correct just because you want to check it numerically, but there's no logs here, so you don't have a function that has domain issues. Okay, so you're probably okay not checking. Okay, all right. Now, most of the time you can't get the base to be the same. So like on one like 43, I'm going to do a bunch of these. On 43, okay, watch when you copy it to make sure you get the 0 in the right spot. I can't get the bases to be the same. So this is the kind, and I really want to see you doing this. I'm going to log base both sides. And because this is an E, and I have a log base E on my calculator, that's what ln is, I'm going to natural log both sides. And I should see that on your paper. You shouldn't skip that. Okay, but because ln is really log base E, it's really this, it undoes the exponential base E, and you're left with just a negative 0.497t. Okay. Now, I like the thing with the variable on the left, so if you don't mind, let me just switch that. Because what I'm trying to do is get the t by itself, and I'm almost there. I'm going to just divide on both sides. And then sometimes they want like the exact answer. That's it right there. That's the exact answer. So this is what you could put in for the exact answer. T would equal that. And then if they ask you for the decimal approximation, you put in ln of 2, close the parenthesis, and don't forget to divide by a negative 0.497. And so that's going to be about negative 1 point. And double check, because these come from different books. What did they want? Nearest thousandth. That's 3 places. Okay, I'll go back and fix that. That's part of the reason you show your work. So it was negative 1.39466 and all. So if I'm rounding to the thousandth, I'm going to bump that up to a 5. Okay, so that would be the exact answer, and this would be the decimal approximation to the nearest thousandth. Okay, and because this had a base of e, there was a real advantage to using natural log. Okay, all right, let's do another exponential. Let's look at x to the said it backwards, 5 to the x plus 3 equals 814. Anytime you got a variable in the exponent like we did on 43, okay, logs are going to be involved most of the time. So on this one, I can see 5 would go into 814. There's no point in trying to get the bases the same. So what we learned to do is come over here and do the log of both sides. And there's no real advantage because we were using that approach that'll work for most folks, no matter what your calculator. Okay, and so we're just going to come in and we're going to log both sides. Okay, the thing is, this x plus 3 right here, okay, can now be brought down in front using property 3 of exponents. And this is huge. It changes your exponential equation into a linear. It just doesn't look like it to you, but log of 5 is some number, log of 814 is some number, okay? So we could on this one, since there's not a number in front of the x, we could just go ahead and get rid of the log of 5. Now log, log is the name of a function. I shouldn't see you crossing out the logs. You can cross out the value of the function at 5 though. And that leaves you with x plus 3 equaling the log of 814 divided by the log of 5. And you can't come in here and divide. So that's part of it. Now you're really close. You just need to subtract 3 from both sides to get x. So x, the exact answer would be this. Okay. Now you type that in if they want a decimal approximation. Make sure you use log if that's what you did the first time. Use the log in both spots. You could have used natural log just as easily. And we would get that to be approximately 1 point, and let me check. This one said for some reason round to 2 decimal places. This is kind of what it was, and there was more. Round to 2 would be about 1.16. Exact answer, and then decimal approximation. It's number 44. Okay. All right. Now let me go ahead and jump to an application problem that deals with exponentials, and then I'll stop the video, then I'll do one on logarithms. Okay. So on 49, we have a model, okay, that models the population of a U.S. state in millions T years after 2000. So T would be the number of years past the year 2000. So on part A, it says, what was the population in 2000 itself? Okay. So for that one, you should be thinking, well, that's 0 years from 2000. So let's plug in a 0 for the T. And when you do, okay, that's going to be 24.2 e to the 0 power. That's 24.2 times 1, since a 0 exponent on something gives you a 1. And so that's just going to be 24.2, and it's really 24.2 million. Okay, so that's part A. That's just a function notation problem for the most part. Just plug into the function. B is the one that requires a little more work. It said when, in what year will the population reach, what was it, 31.4 million. Okay, and the question was, when would the population reach 31.4 million? So what you're going to do is you're going to plug in the 31.4. That's what the population turns out to be. Okay. So what you got now is a logarithmic equation. So be sure you isolate the exponential part first. Don't log too soon. To do that, you're going to divide the 24.2 on both sides. Okay. All right. And then at that point, I have this, and you could divide it, but it's kind of dangerous. Like in engineering, you would not want to. You'd want to keep your accuracy. So I kind of leave it normally. Okay. But now I'm trying to undo an exponential function that has a base of e. So I'm definitely going to use ln. And you should show me that ln on each side. Quit skipping steps. And so the natural log is log base e. It undoes the base e, and you get the 0.0775 t equaling the natural log of this. And by keeping that like it is, you're not going to introduce any round off error. Okay. Now, really though, at some point, if you felt like it, you could just take the 31.4. Let's go ahead and do that. And you could divide by the 24.2. All right, when you do, you're going to get a decimal. And what I'm going to suggest is that you just don't round that decimal very much. Keep a lot of places. Let's go to like 4 so that we don't introduce too much of a round off error. Okay, so now I'm going to natural log that. And like I really keep the whole thing on my calculator when I do the natural log. But it'd be okay to do natural log of that. Just keep a lot of decimal places. Okay, just keep a bunch in there. Okay, now I'm going to divide that by 0.0775, and you got to watch when you're typing that in not to leave off that 0 after the decimal point, 0.0775. And now, and these should have actually from right here, I rounded. Okay, and then that turns out to be like 3.36, and you might have something slightly different depending upon how many decimal places you rounded in here. When I go back to read it, it said round down to the nearest year. So even though that says a 6, it didn't want me to use my usual rounding. Oh, it said nearest year anyway. So this is the nearest year. So that's less than 5. So it'd be 3 years. Okay. And it's 3 years after 2000, right? So my answer should be 2003 on that part B. Okay. All right. So let me stop that. That's the chunk of the exponential